My name is Professor Prof Orata, and we are continuing with our series of lectures in thermodynamics. Today we look at PV work. We look at PV work, pressure volume work, PV work, pressure volume work. And what are we talking about? In PV work, we think of a cylinder. Let's call that a cylinder. And we have what's called a piston. And this piston is enclosing this gas in the cylinder. And this we call a piston. So this is particularly common when you're dealing with internal combustion engines, that is in vehicles. We have this type of setup. So we have a piston and we have a cylinder and we have gas inside that particular system. Again, this is your system. It's that part of the universe in which you have special interest, like we have discussed in the first lectures, one of our first lectures. Now, in this piston cylinder model, which we are going to use to discuss the pressure volume work, there are certain assumptions which you have to make with respect to the piston. One, we have to assume that this piston, which we are having here, has no mass. We are assuming that the piston is massless. The other second assumption about this piston is that it is rigid. The other assumption is that it is perfectly fitting. And finally, that it is frictionless. So those are key fundamental assumptions about this particular piston to make our life easy in terms of calculations in relation to pressure volume 1. We are assuming the piston has no mass, so we don't have to factor in the element of mass there. We are assuming that it is rigid. That means it is not collapsible. Think of it, if this particular piston was like a balloon, it would be collapsible, so that if the pressure of the gas inside here is greater, then what we'll have is the bulging of the piston. It will bulge like a balloon. So we don't want that. We want it to be rigid. And we want it to be perfectly fitting. In other words, gas does not escape by the sides of the piston, where the boundaries between the piston and the cylinder. So it must fit perfectly and is frictionless, so that you don't have to worry about frictional forces in terms of Reynolds numbers and so forth. So we are assuming that that is the characteristic of that particular piston. Now, if we have a situation where the pressure of the gas in the cylinder, which we call P internal, is different from the pressure external pressure external. And what is this external pressure? External pressure can be thought of as the atmospheric pressure. In fact, you can mimic it. You can assume that this external pressure can be represented by some mass, like you have some mass M on the piston. You mimic it with a mass M on the piston, so that we are able to get the mathematical expressions for this. So that if the internal pressure is greater than the external pressure, the internal pressure is greater than the external pressure, that is, external pressure is greater than the internal pressure, we are going to have the piston pushed downwards. In other words, we'll have a compression. We'll have compression of the gas. On the contrary, if the internal pressure is greater than the external pressure, then the piston will be pushed upwards, so that we'll have an expansion. So we talk of PV work, so we are talking of compression or expansion of this particular gas. Now, we have said that this external pressure, you can mimic it to some mass which we call M, so that the force associated with that is mg. Force associated with that will be mg. Now, we have already talked about work. Let us now remove this particular piston cylinder model which you have there. We have already said that work is given by force times displacement. So in this particular case, where we have the external pressure and internal pressure differing by large amounts, so that if external pressure is greater than internal pressure, then we'll have the piston pushed downwards, the gas will be compressed until, of course, where the pressures balances. If the internal pressure is greater than external pressure, the piston will be pushed upwards until where the pressure is balanced. So that is called irreversible work. That is an irreversible work. Very important to note. That means the difference between external pressure external and internal pressure is significant. We are going to see that this is not the same as in the case of reversible work. So that the work done in this particular process, work we said is force times displacement. Now, the force we have there is mg. Let us now say that this particular piston was at some point here. Let us call it x, that the volume here was x1, and the volume when there was expansion, that is, we are assuming the internal pressure is greater than the external pressure, so the piston is pushed upwards. Volume now is x2, so there's a change in volume here which we call delta V. So we can calculate the work associated with that expansion process. We can calculate the work done for this particular expansion process. And you always remember that work is force times displacement. Always remember that. Now, the force we talked about, we mimic the external pressure with some mass, with the force acting on that particular mass we call mg. But remember, force in terms of pressure is force over area is the pressure, or force per unit area is pressure. So that in place of force, because we are talking of pressure and volume, we can actually replace the force with pressure times area. So that force we can see is basically pressure times area. It's pressure times area. So that what we now have here is we have our pressure, which is force over area, which is force per unit area. So we can replace that with the force there, so that W now is pressure times area times displacement. So that if you work with these particular quantities, what is area times displacement? Let us look at a cylinder. Cylinder is normally represented as surface area. Let's call that A meter squared, and right there, let us call it X. So when you talk of this surface area times that length, that gives you the volume of the cylinder. So the volume here will simply be A times X for this particular cylinder. And so in the same way, the area times the displacement. Because remember this area, which we have mimicked, because we mimicked the piston with some mass pushing down on the gas in the cylinder, so that area is basically corresponding to the area of the piston. And if you multiply that by the displacement, then it gives you the volume change. That gives you volume change. So that basically W is pressure times the change in volume. So that W can be written as W is equals to pressure external times the change in volume. This expression we have there is the expression for calculating work in an irreversible process involving piston cylinder model for PV work. Now, what does that mean? What it means is that in this particular case, the difference between the two pressures, like we had already mentioned, is significant. So that if external pressure is greater than internal pressure, the piston is compressed until where the forces are balanced, the pressures are balanced. If the internal pressure is greater than external pressure, again the piston will be pushed up until where the two forces are balanced. It's irreversible. So the piston is not going to come down or go up, depending on which one was greater than the other one. So that's an irreversible process. So this is the expression for calculating irreversible work. If there is irreversible work, then there must be reversible work. And so what does that mean in terms of the change in the dynamics of the discussion? Let us look at reversible work. Reversible work. First of all, before we look at reversible work, we must define what is reversibility in thermodynamics. When we talk of reversibility in thermodynamics, it simply means that infinitesimal modification of a variable reverses the direction of a process. Let us illustrate that. So, in the case of reversible process, what we are saying is that this external pressure and internal pressure differ by very small amount, infinitesimal amount, so that if external pressure is greater than internal pressure, you will not even realize that there's movement. The difference between them is infinitesimal. In other words, external pressure can be related to internal pressure as pressure external is equals internal pressure plus dP. And like we have said, infinitesimal quantities are very tiny quantities. They are not delta. We are not talking about measurable quantity. We're talking about small quantities, so that even if the external pressure is greater than internal pressure, or internal pressure is greater, you will think the piston is not moving. In other words, the piston will look like as though it is quasi-static. Piston will look like it's quasi-static. In other words, if the movement is infinitely slow, it appears like it's quasi-static. So how does this affect our calculation? Now we are talking of the difference between the internal pressure and the external pressure being very, very small. So the external pressure now can be expressed as pressure internal plus or minus dP. But we have already, we know that work. We have already gotten the expression that for work is external pressure times the change in volume, dV. And this should not, this is clear to us, like we have already seen when we derive the expression for external work, because what is pressure? Force over area. So if you have force, pressure is force over area, and then we have volume. Volume is area times displacement. So the areas cancel out, your force times displacement, and that is work. So that's the expression for work. Always remember that W is equal to P dV. That's pressure times the change in volume. So if we replace external pressure with the expression relating the internal pressure and external pressure under reversible expansion, then we have W will be equal to pressure internal plus or minus dP multiplied by dV. If you open up this particular bracket, then you will see that W is equals to internal pressure dV plus or minus dP times dV. Now, the pressure in this second term is infinitesimal, the volume is infinitesimal. So this is a doubly infinitesimal term which can be assumed to be zero. We say it's doubly infinitesimal. And so you can assume it to be zero. So we can assume to be zero. Therefore, what we are saying is W is equals to pressure internal dV. Pressure internal dV. And so, if pressure internal now comes into play, when pressure internal now comes into play, then we have to realize now that we must get an equation of state to take care of this internal pressure. What's an equation of state? Like the one I mentioned in lecture 1, where we say that PV for an ideal gas is equal to nRT. This is referred to as an equation of state. So since we are talking of internal pressure, which you know very well that when the piston moves up, the volume increases. And based on Boyle's law, if the volume increases, the pressure decreases. If there's compression, then the volume decreases, then pressure will increase based on Boyle's law. So it means that since internal pressure has now come into the equation, we must get an equation of state to relate pressure to volume. And we choose the ideal gas equation of state. The other equations of state, the Rayleigh-Kwong state equation of state, the Pettit-Bridgman equations of state, the Bartolotti equation of state, but we choose the simple one, that's the ideal gas equation of state, so that in place of internal pressure, so that we can replace internal pressure with nRT over V. So that W now will be nRT over V dV. Remember, this is P. And so, using a very important identity in calculus, always note that when you integrate dx over x, you get natural log of x plus c. What's natural log? ln, that is log to base e. And remember, e is 2.718. That's not log to base 10. If you have to convert it to log to base 10, you have to multiply by 2.303. So if we use this identity in place of dv over v, if we integrate both sides, then what do we get? What do we get now? We get that w. On integration, we get that w will now be given by nRT natural log of v1, vi, vf over vi. Then when we integrate this particular quantity, we are going to get that as natural log of vf over vi. That will be the expression for work for reversible process. So W for reversible process will be nRT natural log of vf over vi. Very important for us to note that. So that the expression for calculating reversible work, that is where the internal pressure differs by infinitesimal amount compared to the external pressure, is nRT natural log of final volume over initial volume. The expression for calculating W irreversible work is pressure external delta V. Now, this work which has been done based on pressure volume expansions can be represented in an indicator diagram. The work can be represented on an indicator diagram, what we call indicator diagrams. These were used by James Watt for steam engines, early physics. And so this indicator diagram simply shows you what work has been done. And the axes are pressure versus volume. Pressure versus volume. So if you just do the dimension analysis like we said, if you multiply pressure by volume, I repeat once again, pressure times volume, you have force over area times volume. Remember, volume is area times displacement. Then in that case, you are going to have work, because you're going to have force times displacement. So what does that mean? That means that the area under the curve will give you work. So for the irreversible work, if we have the plot for irreversible work where it is carried out under constant temperature, for example, then you are going to have, for irreversible work, you're going to have that external pressure was constant. So the work, if it's from volume 1 to some volume 2, then the area shaded represents the work done for irreversible process. Irreversible process. W reversible, the area shaded under that curve. Remember that? But for the case of reversible work, then this area which was excluded now is included, so that W reversible is the area under that whole curve there. Reversible. the area under all this curve will be there for reversible work. So we see that W, reversible, is much greater than work obtained under irreversible conditions. And this is gotten purely from the indicator diagrams. You're going to see later on when we talk about adiabatic reversible work and adiabatic irreversible work that the quantities, the indicator diagrams differ significantly.